Hi everyone, welcome back to Chem Story. Today, we're diving into a key concept in stereochemistry, prochirality. We'll look at what reface and sci-face mean and how the pro-R and pro-S system works. These terms help us understand how an achiral molecule can become chiral during a reaction. I know prochirality can sound a little abstract at first, but once we walk through it step by step, it'll start to click. Usually, when we talk about chirality, we think of molecules that already have a chiral center. But some molecules are just one small change away, and that's where prochirality comes in. If a reaction creates a chiral center from an achiral molecule, we need a way to describe that shift, and that's exactly what these terms do. Alright, let's get started by looking at reface and sci-face. For sp2 hybridized carbons, like the carbonyl carbon in a ketone, the molecule takes on a trigonal planar shape. That gives us two distinct faces, an upper face and a lower face. And the thing is, those two sides aren't the same. Which face a reaction happens on actually determines the stereochemistry of the product. Now, instead of describing the stereochemistry of the carbon atom itself, we use something called reface and sci-face to tell the two sides apart. To figure out which is which, we apply the Cahn-Ingold-Prelog priority rules, the same ones we use for assigning R and S configuration. These rules help us figure out how a nucleophile or electrophile will approach and attack the molecule. To figure out whether a given face is the reface or the sci-face, we just follow a simple, step-by-step process. First, we assign priority numbers to the three groups attached to the sp2 carbon using the usual Cahn-Ingold-Prelog rules. So, the group with the highest priority is number 1, the next is 2, and the lowest is 3. Then, we imagine looking straight down at the flat molecule as if we're hovering above it. Now, look at how the sequence from 1 to 2 to 3 flows. If it goes in a clockwise direction, then the face we're looking at is called the reface. But if it moves counterclockwise, that face is the sci-face. It's a really helpful trick that lets us predict which side a reaction might happen on, especially when we're dealing with flat planar molecules. Now let's apply those rules to an actual molecule. In this case, we've got a carbonyl group along with an ethyl group and a methyl group, all attached to the same sp2 carbon. Using the CIP priority rules, we assign priority 1 to the carbonyl group since the double-bonded oxygen takes top rank. Priority 2 goes to the ethyl group, and the methyl group gets priority 3. Next, we imagine looking straight down at the molecule, right at the flat sp2 carbon. Now follow the path from 1 to 2 to 3. If that path moves in a clockwise direction, that means the face we're looking at is the reface. So in this case, the upper face is the reface, and the opposite side, the lower face, is the sci-face. Now that we know how to tell the difference between the reface and the sci-face, let's talk about why that actually matters in a reaction. When a nucleophile or electrophile attacks a prochiral sp2 carbon, the side it comes in from, the face it chooses, is what determines the stereochemistry of the new chiral center that forms. In other words, which face gets attacked decides whether we end up with an R or S configuration at that carbon. Let's take a closer look at a specific example, the reduction of acetophenone. In this molecule, the reface is the side of the flat carbonyl group that's facing toward us, and the sci-face is the side that's pointing away. Now, imagine a hydride ion, H-, coming in to attack. If it approaches from the reface, the product we get is an alcohol with the S configuration. But if the hydride attacks from the sci-face instead, then the product ends up with the R configuration. This example really shows how important that point of attack is, because it directly controls the stereochemistry of the final product. So far, we've been talking about re and sci faces in flat planar molecules, but what about when we're dealing with an sp3 carbon that has two identical groups? That's where the pro-R and pro-S system comes in. If you've got an achiral sp3 carbon and two of its substituents are the same, replacing just one of them can create a chiral center. To describe which replacement leads to which configuration, we use the labels pro-R and pro-S. Basically, if swapping out one of the identical groups gives you an R configuration, we call that group pro-R. If the replacement gives you the S configuration, It's Pro-S. To assign Pro-R and Pro-S the right way, there are a couple of key things to keep in mind. First, the priorities of the original substituents have to stay the same when the conversion happens. You don't reshuffle the whole thing. Second, the group you're adding, the one that replaces one of the identical substituents, always gets higher priority than the group it's replacing. That way, you can consistently figure out which of the identical groups is Pro-R and which one is Pro-S based on whether the result ends up as R or S after the swap. If swapping out a particular hydrogen leads to an R configuration, then that hydrogen is labeled Pro-R. On the other hand, if the replacement gives you an S configuration, that hydrogen is Pro-S. This kind of terminology is super useful when we're trying to describe stereochemical changes, especially in cases where chirality is introduced into a molecule that started off achiral. Let's apply this to a real example. We've got a prochiral molecule where the central carbon is bonded to two identical hydrogen atoms, a methyl group and a hydroxyl group. That setup makes the carbon prochiral. Now, to figure out which hydrogen is Pro-R and which one is Pro-S, we look at what happens when each hydrogen is replaced. If we replace the pink hydrogen marked in the diagram with deuterium, the new chiral center ends up with R configuration. So in this case, that pink hydrogen is the Pro-R group. On the other hand, if we replace the orange hydrogen instead, the resulting stereocenter has the S configuration, which makes that one the Pro-S group. So what does all this tell us? Prochirality gives us a way to predict how an achiral molecule can turn into a chiral one during a reaction. Reface and sci-face help us describe which side of a planar molecule is being attacked, and Pro-R and Pro-S help us track how a simple substitution at an sp3 carbon can introduce chirality. These tools are especially useful in asymmetric synthesis and drug design, where getting the right stereochemistry really matters. And once you get comfortable with prochirality, you'll start to see how much control it gives you over reaction outcomes. That's it for today's lesson. See you next time.